Welcome to my YouTube channel. In this lecture, we are going to solve questions 81 to question number 90 from sample paper number 7, BALI navigation book. I hope you have understood the previous questions that I solved in my previous video lectures. If you have any doubts or questions, let me know in the comment box of any of the videos. I'll definitely get back to you. So now let's begin with today's new question, question 81. Frequency and wavelength of radio altimeter is what? So remember, your radio altimeter works in the frequency band of super high frequency, and the super high frequency band is 4.2 gigahertz to 4.4 gigahertz, and the corresponding wavelengths are in terms of centimeter. Are in terms of centimeter. Very important. So 4.2 gigahertz, 4.4, yes. 7.14 meter, 6.82 meter, wrong. So this part of the answer is wrong. So option is wrong. 4.2 megahertz to 4.4 megahertz, wrong. It's 4.2 gigahertz. So left with option Charlie. 4.2 gigahertz to 4.4 gigahertz, 7 centimeter to 6 centimeter. So the wavelength is centimetric. So option Charlie. Aircraft takes off from an airport 2 hours before sunset. The pilot flies a track of 090, winds 130 at 20, task so and so. In order to return to the point of departure before sunset. Okay, before sunset, that means you have 2 hours of flight time to go and come back. The furthest distance which may be traveled is equal to what? So, indirectly they are asking us to find out point of no return distance. The distance you can go to and come back well within time. So for that we will have to know our ground speed outbound, ground speed homebound, correct? What is the formula for distance to PNR? Endurance into outbound speed into homebound speed divided by outbound plus homebound. In place of endurance, you will have to write 2 hours, and then the outbound and homebound speeds we will calculate it now. So let's say this is your departure point, this is your destination. So you are flying from A to B. This is your point of no return. The outbound track is 090. Track 090. So return track will be track 270. This is your aircraft flying outbound. At a task of 100 knots, winds are coming from 130 at 20. So 130 at 20. So winds 130 at 20. So now we will use CX3 to find out our outbound ground speed. Go to wind correction option. As 100. Course 90. Wind speed 130 at 20. 90 degree. Wind speed, wind direction, wind 130. Yeah. So wind direction is 130. Speed is 20 knots. Course is 90. Task is 100. So ground speed will be 84 approximately, and true heading will be 097. So outbound ground speed is 84. Homebound ground speed will be how much? So coming homebound, the track will be 270. Track will be 270. Task same, track 270. Wind speed 20, wind direction 130. So check the values. Task 100, course 270, speed 20, direction 130. So ground speed 114 knots. So homebound ground speed will be 114 knots. Now use the formula. PNR distance will be endurance outbound homebound, outbound plus homebound, So 2 hours into 84 into 114 divided by 84 plus 114. So 84 plus 114 is 198. 2 into 84 into 114 is 19152 divided by 198 is 96.7 or approximately 97 nautical miles. So you can go. So in order to return to the point of departure before sunrise, the furthest distance which may be traveled is what? So you can travel up to a distance of 97 nautical miles in order to come back at your point of departure, place of departure within 2 hours. Okay, so this is your answer, 97 nautical miles. Aircraft has a task of 300 knots and is over a stretch of water between two airfields, 500 nautical miles apart. If the wind component is 60 knots headwind, what is the distance from the first airfield to the critical point? So, there is an island here, there is another island here. So, there is one airport here, departure airport, destination airport is here. Your aircraft has taken off from departure and it's going to destination, and there is a water body separating these two airports. Okay, everywhere there is a water. Now you are flying at a true airspeed of 300 knots. Fine. 500 nautical mile is the distance between them. Okay. Wind component 60 knots headwind. So you are getting a 60 knots headwind. What is the distance from the first airfield, that is your departure, to the point of critical time, critical point? So distance to critical point is equal to total distance between the two airports multiplied by homebound speed divided by outbound plus homebound. So we have the total distance between the two airports, 500 nautical miles. Now let's find outbound ground speed and homebound ground speed. Let's say we are flying a direction of 090 towards destination, and the direction to be followed coming back is 270. Let's use CX3. Or we can, okay, let's avoid using CX3. We can directly find ground speed outbound. How? So ground speed outbound will be true airspeed minus headwind. So 300 minus 60 is 240. Coming back home, okay, coming back, this same wind, which is a headwind going towards destination, will serve as a tailwind coming back. So coming back, your ground speed homebound will be true airspeed plus tailwind. So 300 plus 60, that is 360. Now let's use the formula. Critical point equals to 500 multiplied by homebound speed divided by 360 homebound plus outbound. So 500 into 360 is 1,80,000 divided by 600 is 300 nautical miles. So correct answer is 300. Distance to critical point is 300 nautical miles. Preventative Resolution Advisory in TCAS is what? Maintain vertical speed, crossing maintain, monitor vertical speed. So your TCAS will generate two types of resolution advisories. Resolution Advisory 1 and Resolution Advisory 2. Let's say Resolution Advisory 1 will be called a preventative resolution advisory. The resolution advisory number 2 will be corrective resolution advisory. In a preventative resolution advisory, you will be asked to monitor your vertical speed. You will be asked to monitor the vertical speed of your aircraft. In the corrective resolution advisory, you will be asked to change your vertical speed of aircraft, to change the vertical speed of aircraft. So what happens in preventative? Let's say this is your VSI, vertical speed indicator. So there will be, whenever preventative resolution advisory is issued, a part of this vertical speed indicator will be shaded red, will be shaded red in color, and the remaining part will be shaded green in color, like this. So your job as a pilot is to maintain or to keep your vertical speed in this particular green color band. Okay, any vertical speed, but that vertical speed should be limited within this green band. You should not have a vertical speed which is anywhere in this red color band. Okay, so make sure your vertical speed is anywhere in this green color band. So that is called preventative resolution advisory. In a corrective resolution advisory, you will be asked to climb, you will ask to increase your climb if required. Similarly, you will be asked to descend, you will be asked increase descent, okay, as required. So these are corrective resolution advisory. So the correct answer is option Charlie. Monitor vertical speed. Keep monitoring your vertical speeds. Make sure that you are in this green color band. Purpose of latitude nut in DGI is to what? Correct earth rate compensation, correct transport vendor, correct real vendor. So the latitude nut given in directional gyro indicator is to correct for earth rate compensation error. 86. NDB transmits a signal pattern in the horizontal plane which is a beam rotating 30 Hz omnidirectional cardioid. So correct answer is option Bravo. Your NDB ground station, your NDB ground station will transmit a radio beam which is omnidirectional in the signal which is omnidirectional in direction. Okay, it is the job it is the job of the sense aerial located on your aircraft, find out exact direction from where the signal is originating. Okay, so omnidirectional is the answer. Next, the middle marker of an ILS installation identifies itself with dots and dashes with alternating amber light, continuous dots white light, continuous dashes amber light. So you have three types of markers associated with an ILS: outer marker, middle marker, right, and the inner marker. Now the outer marker is blue. Remember blue, amber, white, blue, amber, and white. And the Morse code for outer marker it is continuous dashes. For middle marker it is alternating dashes and dots. For the inner marker it is continuous dots. Okay, so they are talking about middle marker. So it's alternate dots and dashes with an amber light. So option A will be the right option. 88. Aircraft takes off from an aerodrome called Alpha, whose altitude is 483 feet, QFE is 963 millibars, temperature 32 degrees Celsius. 5 minutes later, passing 5000 feet on QFE, the second altimeter set on 1013 will indicate approximately what? So when you set 1013 in your altimeter, you get pressure altitude indicated. Okay, so let's draw this airport. Now the QFE, 5 minutes later, 5000 feet on QFE altitude. QFE is 963. Mean sea level QNH will be what? Altitude of this airport is 483, right? So now the difference in height, this height difference can be converted into corresponding, it can be converted into pressure difference. So what is the height difference? It is 483. Now we know that 1 millibar equals to 27 feet of height difference. So how many millibar will be equal to 483 feet height difference? So it will be 483 divided by 27, that is 18 millibars, approximately 18 millibar. So the QRH pressure will be equal to 963 plus 18. 963 plus 18, that is 981 millibars. 981 millibars. Why more than QFE? Because when we go deep in the earth, atmospheric pressure goes on increasing. Okay, so we have used this elevation to find out this pressure level. Now standard pressure setting 1013, which is even more than 981, will be below this QNH level somewhere here. Standard pressure setting 1013. Okay, next. Your aircraft is 5000 feet on QFE. That means 5000 feet above the aerodrome. So let's draw your aircraft here. So it is 5000 feet above the airport, equals to 5000 feet. What will be its altitude? Its altitude will be 5000 plus 483. So 5483, that will be its altitude. What will be its pressure altitude? Its pressure altitude will be altitude plus this extra height between QNH and standard pressure setting. Now what is that equal to? Now the pressure difference between 1013 and 981 is 32 millibars. That is equal to a height difference of 32 into 27, 864. There is a difference of 864 between these two pressure levels. So your pressure altitude will be this whole thing. So it will be equal to 5483 altitude plus 864 difference between two pressure levels. So 5483 plus 864, approximately 6350 feet. So the pressure altitude will be 6350 feet. Okay. So the altimeter which is set on 1013 will indicate pressure altitude. The altimeter which is set on QFE will indicate 5000 feet. Simple. How do you measure your location using GPS? Simultaneous bearings, range and bearings, simultaneous ranges. So if you look at the principle of operation of GPS, GPS gives us location by measuring simultaneous ranges from a number of satellites. When descending through an isothermal layer, so it's an isothermal layer, that means temperature is going to remain constant in that particular layer. You're descending at a constant Mach number. The true airspeed, calibrated airspeed and local speed of sound will be what? Okay. So let's draw this diagram. So let's say this is your Earth, and this is the isothermal layer above your Earth's surface, where the temperature is 30 degree Celsius. Okay. Now your aircraft is descending. Aircraft is descending at a constant Mach number. Now first things first, when you descend to lower and lower altitudes, what happens to your atmospheric pressure? Atmospheric pressure increases. Atmospheric pressure increases. Now your calibrated airspeed is nothing but output from your airspeed indicator. This airspeed indicator is a pressure instrument. It's a pressure instrument. And this pressure instrument requires what for its working? It requires atmospheric pressure, correct? Namely, it requires dynamic pressure. This dynamic pressure is represented to us in the form of calibrated airspeed or indicated airspeed. Now, when you go to higher and higher altitudes, what happens? Atmospheric pressure decreases in value. Okay, it reduces in value. So that means when you go to higher altitudes, less and less atmospheric pressure will be available for your airspeed indicator to use. Okay, to use and work out and show us our airspeed. So less atmospheric pressure available. That means less dynamic pressure registered, and less dynamic pressure is registered, that means less calibrated airspeed will be indicated to us. Opposed to this, when you come down to lower and lower altitudes, atmospheric pressure goes on increasing. With increase in atmospheric pressure, the dynamic pressure available for registration will also increase, right? So more dynamic pressure, more inputs will be equal to more outputs. So if more dynamic pressure will translate into a more calibrated or a greater calibrated airspeed indication. So that's why when you come down to lower altitudes, when you descend, atmospheric pressure increases. Automatically, this increase in atmospheric pressure will influence your pressure instrument, your ASI, and your airspeed indicator will show a greater and greater airspeed. Okay, so what will happen to calibrated airspeed as you come down to lower altitudes? It should increase. So increase, gas, increase. So Bravo is wrong. Now let's look at local speed of sound. Now since it's an isothermal layer, the temperature in this layer is going to remain constant, 30, 30, 30, 30 everywhere, 30 degrees Celsius. The local speed of sound equals to 39.17 square root of temperature in Kelvin. So that will be equal to 39.17 square root of 273 plus 30, 303. Now square root of 303 multiplied by 39.17 is 682 knots. So the local speed of sound is 682 knots. This sound will remain constant throughout this isothermal layer because the temperature is going to remain constant in this layer. And local speed of sound is proportional to your temperature, right? So if temperature is constant, local speed of sound will also remain constant. So what will happen to local speed of sound? Remain constant, decrease. So it's going to remain constant. It cannot decrease. So this is also eliminated. We are left with option alpha. So that means your true airspeed. Now, your Mach number equals to true airspeed divided by local speed of sound. Now you're descending at a constant Mach number. So Mach number 0 0.5, 0 0.5, 0.5, everywhere 0.5. So constant Mach number. Local speed of sound is also going to remain constant in this isothermal layer. So local speed of sound also constant. So your task will therefore be also constant. That will also not change. You will descend at a constant true airspeed. Okay. So that's why it remains constant. Calibrated airspeed increases. Local speed of sound remains constant. Important conceptual question. So I hope you have understood all the 10 questions in this video lecture. I wish you very all the best. Keep practicing these questions again and again. Watch other lectures that I have made and uploaded to my YouTube channel. I have uploaded questions from Keith Williams' performance book, and in that I have solved so many questions which are similar to this particular question: descending in an isothermal layer, descending in an inversion layer, climbing in an inversion layer, so on and so forth. So do watch those performance lectures, very important performance questions for your CPL, ATPL, and type rating. Apart from that, you can also watch my payload questions. I have solved payload questions from Keith Williams, from other sample papers, also CPPNR videos from Oxford and RK Bali as well. So explore the channel and do watch all the relevant videos. Subscribe to this channel if you haven't yet. Hit the like button and share this video lecture with your friends. Best of luck. See you in my next video.